cautious beyond, if the person you talk with doesn't have an exam, I'm going not discuss it. Hopefully this will be taken care of shortly. That's why I was holding off last week. I kept hoping to resolve this, but so far I haven't. Okay, so what I want to do first of all is to look at, I want to look at, just see where we stand with respect to the syllabus. I have notes for Section 2 and Section 3, and we were working on Section 2 last time. Section 3 is on regular expressions, and it gets a little tricky. So we're going to look at Section 2, and we may get to Section 3 and do some of it. I don't think we'll finish it today. So I want Section 2. Let's I need to go back here. Chapter 5, Section 2. Now we started this last time. I'm going to set the working directory to this. Let's just see. I'm gonna clear this. I'll blow this up. It's preparatory work here. So we actually needed to load this package, our bioinformatics or bioinf. So I'm going to execute that. And I'm going to go ahead and actually execute this whole file just so we can refer to it if we need to. So this gives... So last time I went through some of this first part, and where I actually did this where I randomly sampled DNA. So if I have random DNA, if I actually look at the random sample of DNA, I got that. And now what I'm going to do, there's a substring function, and what I'm going to do is I'm going to subset that into groups of 3. And so the string I want to subset is the first argument. The second argument are the start values, and the third argument are the stop values. So, for example, a sequence from 1 to 102, will start out at 1, it'll be 1, 4, 7, and so forth. And then the sequence starting at 3 will then go, it will go by 3, 6, 9, and so forth. So those tell the end. So I'll take the first of the second argument with the first of the third arguments. So that will be a 1, 3. So it's going to subset 1 to 3. And then the next one will subset 4 to 6. And then the next one will be 7 to 9 and so forth. Is that clear? So if I do that, if I run this and print this out, you can see that it broke it up into those triplets. Now with DNA, if you take each of these triplets, they map to a particular amino acid. So there's a mapping between the DNA in triplets, and what it forms is certain, in proteins, or the building blocks of proteins, certain amino acids. And so from that, you can actually map, what's called the genetic code, and that's the mapping from these triplets to particular amino acids. So it basically gives it's sort of like an associative array where it gives you a lookup for what the corresponding, I don't know exactly how they implemented it, but I'm going to sort of find, this is really weird because sometimes this works and sometimes it doesn't. It worked last time. And I haven't quite figured out. I thought it was in bioinf, but it's not finding it. And sometimes that's happening, and I don't know, maybe it's another package I have loaded that I need to find out where it is. At any rate, actually last time I did this and it gave the amino acids. I need to find out where this actually comes from and make sure I've loaded the package. I thought it was in the RBioinf, which I just loaded, but or did I? Did I load it in the right place? Let me check. Let me do this again. Yeah, I did. Unless I.
Biostrings.
What now?
Biostrings is what it says online.
Oh, it's biostring? Okay. I'm not sure why that was working. I'm not sure whether we have biostring loaded. So that's what? How do you spell that?
Biostring.
All small. I-O.
B is capitalized.
What now? B is?
B is capitalized.
B-I-O-S-T-R-I-N-G-S. Is that what it is? Okay. Well, we do have it on the system. Let's see if it's... Okay, good. Thank you. I know we don't have all of these packages. In fact, there are some packages that later on, and particularly in section 3, we're going to have to add. I don't have them all loaded. The problem is it's sort of scattered throughout the book as to what packages you need. So maybe there's a place in the preface that lists them all. But so, okay. Now, this is a function. So this is a function that's sort of just going to collapse. What this is going to do, this is a function that's going to collapse based upon the collapse equals the empty string. It's going to shove that string together is really all it's going to do. And let's see if this works. And then if I apply the function dna ZAA, if I apply that to, I think, NC is the number of carries a DA sequence. That's, yeah.
It's a 2, not a Z in the function that you wrote.
Oh, that's better because it says DNA to AA. Okay, but this, I'm not quite ready to do it anyway, so I'm going to take this away. That means, a lot of times you use that DNA to something, so it means I'm going to convert it from this to this. Later on we'll see an example of that also. So if we give it a DNA sequence, I think NC, yeah, is the number of characters in the sequence. And if you look at RD, I think that if I apply this to RD, that it will work. Let's see. So if I do DNA 2, whoops, where am I typing? Don't want to be typing there. Let me typing over here. So if I do DNA 2 AA, I think if I apply it to RD, let's see if this works. Yeah. What that did is it collapsed it. So that's the same thing as this, except this function collapses it. The key thing in that code is the collapse equals. It says, what do I use to separate? Well, I'm going to use nothing to separate them, so it collapses it. So a lot of times that's what you want to do. I'd have to look it up and see what this symbol is, what that represents, but that's a real symbol. That's presumably in that genetic code database as to what's actually there. Okay. This example seems sort of pointless because let's see. I think A has, have I defined X? Yeah, it's not even defined. Let's just start here and define X as this. And then I'm going to get a substring I'm going to get a substring, but that is a replacement function. What it's saying is substring is on the left, not the right. And so it's saying a substring of x, a sub-str substring of x, and then it says this is the start, which is 2, and the stop, which is 4, and I'm going to substitute def. Okay? And why did it not print this out as to, okay, oh, because it's a replacement function. So now if we print it out, notice that def, if I look at substring, I actually have a vector of 2 strings, right? I've got howdy as one, and then I've got do they friend. That's my other string. So I've got a vector of strings. So I have a character vector, and it has 2 strings in it. So the length of it is 2. And what it's going to do is actually, the substring is actually going to replace it in both strings. So notice it has h, d, e, f, y. So it looked at the second, third, and fourth position in the first string, but it also looks at the second, third, and fourth position in the second string. And so it replaced in both. So that's one of the ways you can do replacements. There are other ways. Now, paste. I'm going to paste. I have a vector 1, 2, 3, and I'm going to paste it to a vector 4, 4, 5. I'm going to paste. Now it's going to coerce the vectors to character, and then it's going to put the plus signs in. So if you look at it, it's 1 plus 4, and it's going to recycle the second one. The second one is shorter, notice. The first one has 1 to 3, and the other one is 4 to 5. So it's going to recycle the second one. So it has 1 plus 4, and notice the plus is the character that it does this on. Then it has 2 plus 5, and then now it has 3 plus, well, it recycles back to 4, 3 plus 4. Okay. This is slightly more complicated. Here I'm going to paste 1, 1, 4 with a plus sign. The separator is a plus. Then it takes the second element, 2, 2, 5, and it takes the third element, 3, 3, 6. Okay. Now if I do 1 to 4 and I do a collapse on equal signs, it actually collapses it, but it put equal sign. If I would have put double quotes with nothing in it, it would just jam them together. That's what we did previously. We just put double quotes and it jammed them together. Now usually this is a split. This is a string split, so it breaks a string up. And the first argument of the string or the vector of strings you want to break up, and the second argument is the splitting character. In this case, we have 2. So let me tell you how this. Usually, you only have 1. In other words, that second argument usually has just 1 splitting character. So what happens is when you have 2, they get recycled. So what happens? It says AB is going to be split on Y, but there is no Y, so it's not split. Then CDE gets split on the double quotes. And what that does, and this is similar to null, splitting on null, but there is a distinction. The double quotes splits it into C, D, and E. So this by using the double quotes, and usually you may have a string, and your second argument is just double quotes, and it will split that string into individual components, letter by letter or whatever. So when we, Now what happens, we'll continue on. So CDE gets split by the double parens, which creates single ones. But what about, what gets used for X, Y, Z? Well, you recycle, so Y gets used again. It says split on Y. So it splits that third string, X, Y, Z, into X and Z. So in other words, the Y, the double quotes, it recycled for the third one, it recycles back to y. And it splits on y. So it split it into an x and a z. You'll see this splitting function later. It's fairly common. And we can do it in a more sophisticated way, except usually this second argument doesn't have, that's a vector. Usually it's just a single, it's usually like just double quotes where I split it into all possible, all pieces, or some other character I split on. Usually it's just like, double quotes y. It's usually simpler than this. This has, the second argument here says I have two different splitting criteria, and those get recycled. Okay. So I'm going to read lines from this file. I hope this will find it. Okay. So let's take a look at x, which is pretty big. And maybe I shouldn't have done that. I forgot it was that big. So x is pretty long. I'm reading the lines in this file. And so this file path to r.home, I have a file called copying, and I'm going to paste collapsing on /n says collapse on a new line. Okay. So it's actually going to put new lines every time there's a new line. It's going to collapse it all together, but it's going to put new lines. So in other words, this is only, it has a quote at the beginning and it has a quote at the end. So there are no quotes in the middle, but every time there's a new line, it actually puts a new line. Okay. Now the string wrap, the string wrap, one of the problems you have, if you're writing a book and you use sweave, which takes LaTeX into typesetted format, is you get the style file for the book you're writing. It's got certain boundaries. And then LaTeX can have a tendency to write too far into the right margin, so that you have these strings sticking out in the right margin. And there's a function called string wrap, which tells you at what point do you want to wrap it. Now, if you're presenting slides, a PDF slideshow, this is even a bigger problem because slides have fewer characters on them. So we need to make sure we wrap. The problem with this is that this function, string wrap, is actually not quite as good as you would want. And in the book, they reference another function that they wrote in the bioconductor, one of the bioconductor packages, that actually does a better job of wrapping it, at least when you're using this typesetting system called sweave. At any rate, this string wrap, let's look what happened. Here I'm gonna be smart. We'll only print the first 10. And so what happens is we print the first 10, and actually this is 1, 2, 3, 4, 5, 6. I'm sort of wrapping it at what, 30? Yeah, I'm wrapping it at 30, and I'm putting a prefix my idea. So there's my idea, it gets wrapped at 30. So you never have something long. And it also gets wrapped, I think, at a new line. And then if I can write these lines out. Here I'm going to write the lines out, again using 30 of a prefix in mind, and this is just the first 3. I could actually write that out to a file, and it would be a more readable file than the way the original file was done. So now, of course, if you did a margin, what it's doing is using monospace characters. So this is good for code, but the problem is with the font technology that there are certain, like if you have 2 F's in a row, they put less space between them and so forth. So if you have proportional spacing for your fonts, then it may be hard to predict exactly where you want that wrapping to occur. If you're writing computer code, which is monospace, no problem. But a lot of times that I have needed this was with the computer code. So I have this presentation I put up on the board, and I have the computer code. You only see part of it because the rest of it writes off the end. And these types of functions would allow you to force the computer code back. So that's the string wrap. Okay. Now, there's also a function. There are two functions in here I want you to look at. To upper takes whatever the characters are. To upper forces it to uppercase. So if it's lowercase, if it's uppercase, it's already there. But if it's lowercase, it forces it to uppercase. So to upper is a function that forces from lowercase to uppercase. And in character CHARTR, which is character transformation, what this is going to do is in a string, it's going to transform each T to a U. Now, when you're going to DNA to RNA, that's the type of thing that happens. Genetically, you're getting this transformations in the genetic code of T's to U's. And so there are reasons why you might want to see what the RNA looks like. And so we're going to, the first part of this code that says, if it is not a character string, then you say, you stop and say need character string. Then I force everything to upper, and then I transform the T's to the U's. So I'm going to define, this is DNA to RNA. So DNA to RNA. Okay. And so that's a transformation formula. So let's go ahead and execute this function. And then I'm going to take a random sequence of DNA, two of them, one of length 15 and one of length 12. I'll call that X. And so let's look at X. So those are my two strings of genetic code, and I'm going to transform this to RNA. And the way I'm going to do that is, the way that happens is to convert all the T's to U's. And so let's do that. And now if you compare those, notice the T above becomes a U below. So this was a transformation from DNA to RNA. Biological is a process that does that. Biologically, I should say. Okay. Whoops. Here we're comparing sequences, ACTG. Actually, I'm forgetting what this function does exactly. This is doing a transformation. I think it's doing an A to a T and a C to a G. In other words, if you look at DNA, the A and the C bind together in either direction, and the C and the G bind together. And so this is going to convert an ACTG to its complement, which is, I think the COMP means complement. So it's going to take the complement of it, which is TGAC. So if I define this function, we'll define the function, and then X is back here. That is the X we define. And so if you look at the original X and then compare it, every G becomes a C and every T becomes an A. So it's the complement. And again, if you look at binding of DNA, it's, if you look at the binding of DNA, it's the A with the T's and the C with the G's. So it's the complement of the binding that actually exists. I don't know if this this is saying you have a sequence and you're testing whether or not this sequence is DNA. So first of all, you have a sequence. You're going to convert it all to upper, and then you're going to split the screen. Now, what does that? It splits it into null, so it splits it into individual pieces, and then I'm going to S-apply maps this function across this. In other words, it splits XU into all these components, and then I S-apply that across that. And I don't remember if I've tried this or not. I think this X is a sequence of DNA. I'm not sure whether it works on it's because there are two strings here, and so we'll see if it works on, yeah. It tested both of them, and it says they both are valid DNA sequences. So X, remember, had the two sequences that are DNA. You can, it has to contain the right characters. It has an alphabet. If you made a coding mistake or something, the alphabet only consists of 4 letters. So it's basically testing over here, is Z in each of the, is Z one of these 4 letters, A, C, G, or T? Okay, and if Z, if one of those components is not in it, then it's not DNA, because DNA has to have that alphabet. You can't have any other letter. Okay, any questions? Okay. The string reverse, I just think, yeah, what it does is just reverse the order. I think I'll skip that. And this is a reverse complement. It takes string reverse and then it takes the complement. So I think I'll skip these. But what this does, string reverse, reverses the string. And then we have this complement. The next one not only reverses it, but it does the complement of the DNA. So it's combining the function reverse complement takes the string reverse defined here and the complement of sequence, which we defined previously. And it first of all does the complement and then it reverses it. So I think I'll skip that. But now, one of the things that's quite important is sorting. We think about sorting numbers, but you can also sort text. In terms of the alphabet, A is before B, before C, and so forth. So we can actually sort text. If you sort numbers, you know what that is. So you have a numeric sequence, and you have a bunch of numbers, and you're going to sort it from smallest to largest. And there are other options for going to reverse and so forth. So I'm going to set a seed, and I'm going to get a sample of letters. So here's the sample. And now I want to sort those. And now if I sort it, it's in the order you would expect. But you can also do this. You can say, is X, which is a vector, less than M? Well, all those letters are less than M because I did a sample. I did a sample of the first 10 letters. I did a sample of 5 from the first 10 letters. So all of them are less than M, so they're all true. So that's pointing out that I can sort them and I can also do logical operations. Now, I can't add letters, but I can do, I can do manipulations less than or equal, less than, and so forth. And I can say equal, but when you say equal, it's the double equal. When I'm saying something equals something and doing a logical comparison, it's not an equal sign, it's an equal equal, which means a logical comparison in R. Now, genetically speaking, in the DNA, you have things called exons and introns, and there are different areas of the sequence of the DNA. And of course, chromosomes. And so I have these terms, intron, exon, example, and chromosome, and I want to know whether certain things match. And so there are various functions, match, and then there's p-match, and p means partial matching. And then there's also something called character match, and they're slightly different. So I say match, exon, is can you find it in that string? Yeah, you can. It's a second string. In other words, exon is the second one. Now, if I do partial matching, this may surprise you. But why don't we get where this is? The E is in there, right? So what's the problem? It's ambiguous. This match, this p-match, it only finds the first one. There's a second one. It says, it's only going to give you one. And it says, I don't know whether it's the second or third. They both start with capital E. So in this case, it won't do it. But if I say p-match EXO, now that's not ambiguous. EXO is in the second one. It's uniquely determined. EXO is unique, but E is not unique. It's ambiguous as to what to return. If I do I I is okay because that's the only capital I. Now, if I do character match, that's also going to work. But there are some distinctions between, there are some distinctions between. So if I do p match, suppose I have a vector now, p match and int, and what that is finding is it finds an I in the first one, but it doesn't recycle. The p match doesn't recycle. So once you've found it, it looks beyond it, but there is nothing beyond it to find int. Now there is an option in p match that says duplicates are okay, and so if I do that, then it says, oh, I found them both, and they're both in that first sequence. So if I say okay, duplicates are okay. Now character matching, I think, yeah, this character match sort of automatically does duplicates. Okay. Now, if I do p match, again, p match of AB, you would think it would say it's the first and second, but it only finds the first. And character match, I have, let's see what happens with character match. In this case, there's an ambiguity, and that's the reason it turned to 0. So these are a little bit tricky to work with, but so. Now, before we go on to regular expressions, which we'll be doing next time probably, I don't know, maybe we'll get a little bit. It's important to understand sort of special characters. The backslash in R is a special character. And so suppose there are certain, like, okay, if you have strings, they're defined in double quotes or single quotes. Strings are defined in double quotes and single. So suppose you have a quote within a string. You follow me? Like you said, I'm, I apostrophe M. And that's part of a string. But I don't want it to think there's one string that starts. I don't want them to think that I have one string that goes from here to here, and then I don't know what this is because I don't have anything starting it. In other words, by default, it would look at that quote and it would say, oh, that's the end of the first string. But I don't want it to say that. I mean that quote to be an apostrophe. And so what you have to do is put a backslash before it, and then backslash before the quote makes it a real quote. So if you look, if you look at this, it said I'm a string. So the back quote, the back quote works. Okay. So at any rate, now, what about a backslash? Well, a backslash is also a special character, so you have to put a backslash before a backslash to make it a real backslash. So let's see what S is. Now notice it still prints out both. That's because of the way the print works. But if I actually use the concatenate or the cat to print, which is the more normal way, it actually prints it correctly. So this is the way when you define those print functions, a lot of times you use the CAT in your assignment. Your assignments 2 and 3. To actually print summaries and so forth, you'll use the CAT. We see it prints it correctly. But the default print method did not. It printed both of the backslashes. A lot of times you want to remove the quotes. You don't want those quotes. And so the no quote will remove the quotes. Okay. The number of characters in S is 18, and if I do a string split, null. By the way, just to show you, if I go up here and I'm going to go up and I'm going to take this off and just do this. So what is the difference between, I took off the double bracketed 1. String split creates a list. So if you want the contents of the list, and it's a list in the first position here, if you want the contents, you have to go to double square brackets and drill down to the first element. So if I actually want to create a vector, I have to use the double quotes 1, because notice that the first component is this list, but it's the second level down, right? Notice the double brackets, and then the vector is there. So if I really want what's in the first element of the list, I have to do double quotes 1. So remember that string split creates a list, and often what you want is what's inside the list. Now the reason it does that is because you may have multiple things you want to split, and so it creates multiple components. So there's a reason why it does it, but in this case, I want the vector. I don't want the first element of the list, and so that's why I used the double square brackets. Now, what about /n? You would think that that's going to give you the number of characters of /n. In fact, and sorry, that's \n. In fact, it's only one character. It means a new line. And so if you actually do n character of that, you get 1. And character raw, this is sort of the raw encoding of \n. That's the raw encoding. Now, if you're using sort of DOS, PC DOS, to separate, if you're looking at a file, if you're looking at a directory structure, and you're looking at the hierarchy of directories, you get backslashes. Whereas in Unix, it's a slash. So suppose you wanted to convert from the PC format to the Unix format. You want to convert the backslashes to slashes. So if the old, and again I have to use two backslashes because I have to escape it. So the old is a backslash, so I'm going to go from that to this /, and then I'm going to go a character transform from old to new, a function. So here's the function. Did I define that first? I don't know if I did this. So I'm going to define this. So that's fn, is that character string. Again, that would be the way you would have to do it in Windows. If you internally look for the file structure in Windows, and you were using, I mean, a lot of times you do point and click, but in R you want to be able to do character manipulation. So you have that double backslash, and that means it's an escape. So it's really just a backslash. So that's the directory. You're looking at foobar within my documents. And I want to convert to the Unix style. So there it is. That's what it is. So I want to convert character, and I want to go from old to new for that function. And now notice it has the forward. You don't have to escape the /. Okay? So that's the Unix representation. Of course, the reality is you probably want to get rid of that C:, which is a DOS type thing. So later on, we'll learn how to strip things out. So how are we doing time-wise? Okay. I'm almost there. Let's see. Yeah, gsub. Yeah, this is actually doing. Gsub is a substitution. It's going to substitute the second argument for the first. And so it's going to, and the second argument is the new, which has the slash. So gsub is another character string manipulation in which you substitute, you take a string in the first argument and you substitute what's in the second argument for that string. And so that's commonly used, and we'll use it later in the next section. But so the new is the /. Now, those 4 slashes are really only 2 slashes, okay? And so I'm going to do that By the way, I would only need, if I say fixed equals true, that, yeah, okay. There's actually, and we'll talk about this more next time, but there's actually, when you talk about text manipulation, there are really some various standards, and one of them is based upon Perl. And there's a book I bought a number of years ago called Bioinformatics Using Perl, and Perl is a great string manipulation language. Well, R implements the Perl version of this, and if I say fixed equals true, it's equivalent to saying I want the Perl encoding. In that case, I only need the single backslash. I mean, I still have to escape it. So that gives me the same thing by saying fixed equals true. Almost finished here, this chapter. Now, suppose I take text and I want to parse it and actually then evaluate what I parse. So I'm saying that I want to parse the text, and notice that I have mean of 1 to 10 in quotes. So that's a character string. Mean of 1 to 10 is in quotes, so it's a character string. But I'd like to actually execute it. So I can actually parse it, and then V1 it says it's an expression of mean of 0, and then I can actually evaluate that expression, and I get a mean of 5.5. Now I can go the other way. I can take V1 and I can deparse it back to its original structure, and ultimately I can get it back to the character string. So I can both parse text, and then I can, if the text actually represents a function, I can actually evaluate the function, but I can deparse it and go the other way, from the function back to the character string. You may not think that's useful, but in fact it is quite useful. So that actually finishes this it actually finishes 5.1 and 5.2. What I didn't get to, I don't think I'm going to save it, because what I didn't get to, and what I'd like you to look at next time, is regular expressions. Regular expressions are incredibly powerful. So you have to understand that the reason we're doing this, there are a lot of reasons why you want to manipulate text. So we think of, in terms of statistics, you're thinking about, well, I analyze data. And data is either numeric, or maybe it's categorical factors. And I can have interactions with categorical. But data could be text. If I have a document, and I want to analyze the document, then I start out with this long text string, and I have to break it up various ways, and I've got to analyze it. And there's a whole area called text mining, where we mine textual material. What do you think the NSA is doing? They're mining text. They're mining your emails, your Facebook, etc. Okay, that's what's happening. They're doing text mining. Okay, but in genomics, you're mining the DNA, or the RNA, or the proteome. You're mining, we have alphabets for certain biological phenomena, and that we have this coding in DNA or RNA and so forth. And so we want to do text mining there to find out maybe, okay, here we have 2 gene sequences. This sequence is from a patient who doesn't have cancer. This sequence is from a patient who does have cancer. How do they differ? Well, these DNA strands are really long. You're not just going to look at them. Well, you'd be foolish if you did. You're going to use text manipulation to find out where they differ. Okay? So there's a lot of reasons why we want to be able to manipulate text, and that's what we're doing in this chapter. On the other hand, with this 623 course, we do web technologies where you actually scrape in text from the web. We're sort of a mini NSA exercise, where we scrape in, and then we can actually deparse it and break it up and try to make inferences about it. I'm not saying I'm going so far as to say, well, this guy's a terrorist, but the reality is that that's a whole other field. Using a lot of the same tools, though, as we're learning here. Regular expressions are really big, but there's some others we'll use too. But regular expressions are kind of hard, but extremely powerful. So you might want to look that over first. And then you might want to go out and Google. You might want to go to Wikipedia and look for regular expressions, and it's more intelligible. Okay? So that's what we'll do next time. What happened to my record? Did I accidentally close it? Stop recording.